In this example, we're going to be writing a linear and exponential model looking at concentrations of atmospheric carbon dioxide in parts per million. So there's our units. We're talking about parts per million of carbon dioxide in the environment given the year. X is going to represent years, and X is 0 is representing 2000. So first thing I'm going to do is cross out this chart. When I plug in an X value for 2000, I'm going to plug in X as 0. 2025 is really 25 years after 2000, so X is 25. We can do 2050 minus 2000 is 50 years later. And then we have 2075 is 75 years after 2000, and 2100 is 100 years. That way, if we have to plug in 2015, we're not going to plug in X as 2015. We're just going to plug in 15. It's 15 years after 2000. I think crossing that out right away helps to identify the correct X value. The first part says, let X represent years since 2000. We already did that. And use the data from 2000 and 2100 to find C and A to write ourselves an f of X equals C times A to the X and round to 3 decimal places. So we want to write our y equals c times a to the x. Of course, it says call it f of x, so we're going to do that. Our first step is to identify what c is. Well, we're asked about 2 points. So it looks at the points 2000, which is going to be year 0. And the y value there is 410. I'm looking at the chart here. We have 0, 410. And the other point we're told to look at is 2100, which is x is 100. And y is 994. So I'm going to write out our 2 points that we're going to use to create this function, 994. So our first thing is which one is going to give us our c? Well, c is going to be the y value when x is 0. So c for this one is 410. Our second step is to find a. So I'm going to plug into y equals c times a to the x. I'm going to plug in the other point, the one that doesn't have an x value 0. So I'm going to use x is 100 and y is 944 to find a. So the y value is 994. My c, the initial value, is 410 times a to the x is 100. Replacing that x in there. So I'm trying to solve for base A. I'm going to end up having to use my square root button or the X root button under math to take the root here. But before I do, it's 410 times my A to the 100th. So I'm going to divide both sides by 410 to get A by itself. I can plug this into my calculator, 994 divided by 410, and see if it gives me a nice decimal or a reduced fraction. It doesn't really give me a nice decimal, so I'm just going to actually leave it as that fraction. So we get 994 over 410, which I think is easier to write than having to write out a bunch of random decimal places, is a to the 100. So if it was a squared, we'd take the square root. If it was a to the third, we'd take the third root. If it was a to the 7th, we'd take the 7th root. Here we're going to take the 100th root. So I'm going to hit math on my graphing calculator and scroll down and figure out which option has me change the root to any x root. On my calculator, it is math number 5, allows me to change it to the 100th root of 994 over 410, and around to 3 decimal places. So a is going to be 1.00, and that's going to round up to be a 9. And my final step is to write the function. It says call it f of x equals 410 times 1.009 raised to the x. Plug in any x year after 2000, and you can get out to the carbon dioxide in parts per million, which is what we're going to do in the next step. It says use the equation that we just found in part A to predict the concentration in 2125. So how many years after 2000 is that? It's 125 years later. So I'm going to plug in f of 125 for my x value. I'm going to grab my calculator and do 410, parentheses 1.009, and raise it using the caret button above the divide symbol to the 125 power. It says round to 2 decimal places. So I'm getting 1,256.55, and this is carbon dioxide in parts per million. Now looking at the chart, I can see if my answer seems correct. So looking at these outputs, well, the output for X is 100 was 994, and it looks like it's increasing throughout. So it makes sense that the output for 125 would be something a bit bigger than 994. We're at 1256. So it looks like we did a pretty good job plugging in. I'd be concerned if I got an answer smaller than 994, because so far it's been increasing. We have a growth here since our A value is bigger than 1. We have a growth rate instead of a decay rate. Now we're going to utilize our calculator to give us an even better looking function. So we're going to plug this chart in and use exponential regression. So under L1, in my stat, I'm going to hit stat on my calculator, and under L1 I'm going to put 0, 25, 50, 75, 100 to represent those years. And then L2, I'm going to type in 410, 502, 637, 782, and 994. You may have to highlight L1 or L2 and hit clear and then enter before entering these. We're going to enter these in, and then we're going to go over and hit stat again once you have the whole chart entered, and go over to calc and scroll down until you find exponential regression. So under my calc, exponential regression is option 0, which comes after option 9. And I'm going to hit enter a bunch of times so that I can see what this equation is. It doesn't tell us what to call it. It just says round it to 3 decimal places. So I would just call it a regular y equals. And I get 406.726 times 1.00, and that would round to be 9 to the x. So the equation we made by hand in part A looks very similar to the one we just got using our calculator in part C. So we did a pretty good job. We estimated it between 2 points, 2,000 and 2,100, but our calculator does an even better job because it estimates it using all 5 data points. The next part says, well, what if we write a linear function to model between these 2 points? So I'm going to write these as points. F of 0 equals 410. I'm going to call that x1, y1. And then we have the point 50 goes to 637. So I'm going to call that x2, y2. That way, when I write my linear function, which is y equals mx plus b, I can plug right in to that formula for m. y2 minus y1 over x2 minus x1. So for this one, we're going to do 637 minus 410 over 50 minus 0. Difference in y's over difference in x's, we can see that it's increasing. It's going from 410 to 637, so we should get a positive slope, and we do because we get 227 divided by 50, which means m is going to be 4.54. We would say on average, the carbon dioxide in the atmosphere is increasing by 4.54 parts per million per year. If we had to interpret that, we'd say it's an increasing slope with our units. Our second step is to find b. B is whatever the y value is with 0. So b is going to be 410. And lastly, we can write our overall equation, y equals 4.54x plus 410. There's our y equals mx plus b. The last part is really an opinion piece. Which function do you think did a better job of fitting the data? Just between these last 2 equations, I would definitely say the exponential, because we used our calculator and it was a line of best fit between all 5 points instead of 2 points. But in general, when you're choosing between exponential and linear, which one you think it'll be better fitting it, remember exponential grows by a factor that you multiply by, so it'd have to be really fast growth usually, and then linear is just adding a specific number. So you could argue either point, and it would just be an opinion piece. For me, I would say it's exponential because we used the line of best fit. We were looking at all of the points at once, and I would say it's not consistently growing on the table by one certain number where you're adding it. So it makes sense that we multiplied and it was going up exponentially. But you could argue either way, and that would be fine.